Hello, dear friends. Welcome to Math with Amala. Let's start this journey of getting enrichment in the content as well as scores this year with me. Keep following this channel for more updates. Let's start grade 10 chapter 1 real numbers. You must be very familiar with the concept of real numbers that you have already covered in the grade 9 portions. I have divided this chapter into 7 parts, which contains the introduction, Euclid's division algorithm, the fundamental theorem of arithmetic theorem, then example 1, 2, 3, 4, exercise 1.1, revisiting irrational numbers theorem 1.2 and 1.3, example 5, 6, 7, and exercise 1.2. Without any delay, let's move to the introduction part. Real numbers are actually like a mother set for all the numbers, which includes natural numbers, whole numbers, integers, rational numbers, irrational numbers. There are two main concepts which are included in the introduction part. The first one is Euclid's division algorithm, and the next is the fundamental theorem of arithmetic. The Euclid's division lemma states that given two positive integers a and b, then there exist unique integers q and r such that a is equal to bq plus r, where 0 less than or equal to r less than b. R cannot be b, but r can be 0. This is the same as the normal division method. A by b, you will get the quotient q and remainder r. When you get r less than b, you can stop there. 10 by 3 gives the quotient 3 and remainder 1. So simply we can say it like this is something related to the division, like the long division method, and it was proposed by the famous mathematician Euclid. And this is for divisibility of integers. Integers means it can be positive, negative, or 0. So divisibility. Let's take two numbers a divided by b. You will get a quotient and you will get a remainder. Here that remainder must be like less than b. So if we get a number which is less than b, you can stop there. As we know, this is the traditional method of division, the long division method. And also, this method can be used for finding the HCF of two positive integers. If we have two positive integers a and b, then its HCF can be found through this method of long division, where we use the Euclid's division algorithm. Next one is the fundamental theorem of arithmetic, in which we have two cases where we use this fundamental theorem of arithmetic. The first is to prove irrationality of the numbers like root 2, root 3, root 5. The next is explore exact decimal expansion of p by q where q not equal to 0. That means if we have p by q form number, then you can calculate the exact number of decimal expansions where q is used with the prime factorization. Okay. Next we can move to the fundamental theorem of arithmetic, in which we will deal with the statement also. Let's take the prime factorization of 6. You can get it like 6 equal to 2 into 3, where 2 and 3 are the prime numbers. So we can express this number in the form of product of powers of primes. That is 2 and 3 are prime numbers. With the product of these powers, prime powers, we can represent this number. Okay, let's take 1000. 1000 can be prime factorized in this way. 1000, then 2, then 500, 2 again, 250, 2, then 125, 5, 25, then 5, 5. So you can write 1000 is equal to 2 into 2 into 2 into 5 into 5 into 5, which is equal to 2 cube into 5 cube. Okay, 2 multiplied 3 times, 5 multiplied 3 times. You will get 2 cube into 5 cube. This is actually what we mean with the thousands prime factorization. Here we take the power of some prime numbers to multiply and to get the composite number. So let's take some primes 2, 3, 5, 7, 11, 13, 17, 19, 23, likewise 29, it goes. Okay, it continues to infinity. We can take some numbers from this prime set and multiply them together, and then multiply those prime powers together in order to get a composite number. In general, we can say that every composite number can be written as product of prime powers. Let's take some prime numbers like 2, 11 and 17. Let's multiply them. You will get 22 into 17. The answer is 415, 422. Then answer is 374. 374. That means every composite number can be represented in the form of product of prime powers. Here 2 raised to 1, 11 raised to 1, 17 raised to 1. Here 374 is the composite and 2, 11, 17 are the prime numbers. Let's state this as a theorem 1.1, fundamental theorem of arithmetic. Every composite number can be expressed or factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. So we can note two things here, the uniqueness and also the order in which the prime factors occur. What is the uniqueness? Uniqueness means whatever be the number, whatever be the composite number, it has only one representation, or the representation is always unique. Or you can say, if you have a representation, once the order is changed, it is unique, it will not change. Okay, here the uniqueness and the order in which the prime factors occur, that statement is interrelated, because unless the uniqueness is maintained, the order will not be changing. Let's take a composite number. It has one and only one way to represent as a prime power product. Okay, so any composite number has only one way to represent as prime power product. For example, let's take some prime numbers and multiply them. 2 into 3 into 5 into 7. If we change the order, like 3 into 5 into 7 into 2, this is actually the commutative law. Since multiplication is holding the commutative law, these two parts are equal. Even if the order is changed, the LHS and RHS are the same. So you can say the prime factorization of natural number is unique except for the order of its factors. Okay, let's move to the next concept, which consists of the composite numbers representation as prime factor product, prime power product. Let's take a composite number x, where x is equal to p1 into p2 into etc. into pn, where pi's, p1, p2, pn, etc. pn are the primes which are written in the ascending order. The order is kept there, ascending order, like p1 is less than or equal to p2 is less than or equal to etc. less than or equal to pn. Okay, so this is the composite, this is the representation of the composite number in the prime factorization method. In this p1, p2, etc. pn, you may have some primes repeated, so you can give them as the powers. If 2 into 2 is repeated, like 2 is repeated, you can write it like 2 square. If 5 is repeated 3 times, you can write it like 5 cube. Thus, in general, for ascending order, factorizing way is unique always. Thank you all for watching the video. Clear your doubts through comments and please be stay tuned for part 2.